Hello, my name is Ian Ford. I'm a research staff member at Wolfram Research. And in this talk, I'm going to be talking about tracing evaluation, uh, including evaluation chains, trees, and graphs. So the abstract, we're going to be talking about how Wolfram Language models computation using symbolic expressions. We're going to see how once you evaluate an expression, you get a value. You can use the trace functionality to not just get a value, but to get something representing the entire execution history of the program. That can be useful for finding bugs, just exploring, seeing what's happening during the execution. I'll also show we have a few different functions for visualizing a few different ways. There's a few different ways of filtering the execution histories and some tools for manipulation and analysis. So these are the functions I'm going to be covering. Trace dialog, trace print, and trace scan are all system functions since version 2. And resource function, trace tree and trace graph are not yet in the system, but they're useful for visualizing the trace in different ways. So before we talk about evaluation, let's talk about expressions. You may know already that everything in the Wolfram language is represented as an expression. So here's an example. This expression consists of a head, which is the symbol F, and arguments are these symbols X, Y, and Z. So you have the head, bracket, arguments between the brackets. Because of this, you could get expressions within expressions within expressions, and so in general, you get a tree. Here is what this expression looks like as a tree. So we have f of x, y. This becomes a tree where the root node is f. And then you've got these three leaves, x, y, and z. Okay. So those are expressions. You know, expressions can be used to represent data, but they not only represent data in the Wolfram language, they also are used to represent all computations in the language. So here's a pretty trivial one. Here's the expression 2 plus 3. Now, even though this is written in a infix notation, this plus symbol, under the hood, this is still just another ordinary expression. In this case, it's an expression where the head is the symbol plus, and the arguments are the numbers 2 and 3. And here you can see what that looks like as a tree. Okay, now this expression represents a computation. When you evaluate an expression, there's a certain sequence that the Wolfram language goes through to simplify the expression. Here is not the complete list of steps, but the important things. So the very first thing is raw objects like symbols, strings, integers. They do nothing under evaluation. The next thing is you always evaluate the head of the expression. And the examples I've been showing, that evaluation has been trivial because the head is just a symbol like F or plus, but it could be something more complicated that also has to be evaluated. After the head is evaluated, you then evaluate each of the arguments. So this is like time-like recursion in an expression. You have, in order to evaluate an expression, you have to evaluate its sub-expressions. Now the EI, these are like the arguments of the function. These are evaluated sequentially, one after another. So the EI, these are like spatially separated evaluations. Then if the head has what are called attributes, which I will not be covering in this talk, for example, hold first, then you have to modify the evaluation sequence. So this ... there's lots of details there for attributes and some other kinds of transformation rules. But the typical case we care about, we'll have an expression with some head F, and we will use any transformation rules that we've defined for that head, and then finally any transformation rules that are built into the system. For example, the 1 plus 2 example, the way that works is that's the expression plus of 1 comma 2, and we have built-in transformation rules for plus. So this is also something that most Wolfram language users are going to be familiar with, but you can not only use built-in functionality in the system, but you can extend it using your own definitions. So this is an example, simple example of the Fibonacci function, which is of course a built-in, but I'll be using this as a nice example for the remainder of the talk. So we have the initial conditions, fib of 1 and fib of 2 are both 1. And then fib of n for any other n, the way you compute it is by taking fib of n minus 1, fib of n minus 2, and adding them together. So now if I evaluate these and do fib of 5, we get a result. Okay, so that's nice. But what if we want to know, how did it actually get this result? What is actually happening? For example, there may be things going on under the hood that you may not realize. The standard function that you're going to use for this is trace. So trace is a function that evaluates an expression in a special way so that you don't just get the result out, it actually keeps track of every single expression that that the Wolfram language evaluated in the course of the larger evaluation. So here we have fib of 5, and we get this kind of monstrous output with lots of nested lists and things. I'll break it down a little bit here and then go into more detail on the next slide, but you can see it starts out with fib of 5. That's what we started with. And then it ends with 5, which is the value we got. But we also see intermediate steps. For example, after fib of 5, we have a fib of 5 minus 1 plus fib of 5 minus 2. Also, right before 5, where did this 5 come from? Well, it was the sum of 3 plus 2. So if we go through this whole thing, we'll be able to follow how this expression gets broken down into its constituent parts, how the numbers get computed, and ultimately the numbers that get added to give us our final result. Let's break it down a little bit. Let's look at a very, very simple evaluation. If I do trace of 2 plus 3, which is the final step in that evaluation, we see this took just one step. We start with 2 plus 3, we get 5. And this is from the built-in transformation rule for plus. We call this whole list an evaluation chain. And the reason is, referring back to the standard evaluation sequence, once a function has been applied to its arguments, you keep reevaluating the expression. So you will keep applying transformation rules over and over and over again until the expression doesn't change anymore. In this case, it was one step. Let's look at a longer chain. Here's fib of 1 plus fib of 2. So if we trace that, we get this output. Now, how do we interpret this? We see 2 comes from 1 plus 1, but what do these mean? Well, these are actually evaluation chains corresponding to subsidiary evaluations. In order to compute the sum of fib of 1 and fib of 2, you of course have to compute first fib of 1 and fib of 2. So here we see that evaluation chain where fib of 1 evaluates to 1. Then we have another evaluation chain where fib of 2 evaluates to 1. Now that both of these evaluation chains have been completed, we get the results out, 1 and 1. We add them together, 1 plus 1, we get 2. So we can see that we not only get a sequence of expressions, but we actually get nested lists of expressions for the evaluation and its subsidiary evaluations. The nested lists representation is very useful. It's been what we've had since version 2. Wolfram language is very good at manipulating lists, but it can be kind of hard to parse just, visually looking at it. What does this represent? And so I've wrote a couple of resource functions, which may eventually make it into system, which will visualize the output of trace in some more graphically informative ways. So here's a function, trace tree. You can access this by using resource function of trace tree. The exact same expression that we want to trace here, fib of 1 plus fib of 2, but now the evaluation chain is represented a little differently. We still see a sequence here. 2 comes from 1 plus 1, but now we've converted all the nested lists into subtrees. So for these evaluation chains, they become full subtrees. This can be helpful when you want to see how the chains are nested, but oftentimes it's not the chains you're interested in, it's the underlying expressions themselves. And for that, we have another function. Here's a larger tree showing more steps. You start with fib of 3 minus 1, fib of 3 minus 2, compute 3 minus 1 to get 2, then fib of 2 is 1, and so on. If you want to get the connections between the underlying expressions, you can use the function tracegraph. So here we no longer explicitly see the evaluation chains, but we do see the connections between the underlying expressions. So let me read this a little bit. We start with fib of 3. Now this dotted red line represents a place where a transformation rule gets applied. So fib of 3 gets transformed into fib of 3 minus 1 plus fib of 3 minus 2. Now, in order to evaluate this, it needs to evaluate its constituent parts, which is the fib of 3 minus 1 and the fib of 3 minus 2. You see 3 minus 1 is 2, 3 minus 2 is 1, fib of 2, fib of 1. They both give 1, so we get 1 plus 1, which is 2. So this is a nice visualization where you could sometimes see much larger outputs of trace at a glance than in the other forms. We have lots of options for filtering trace, and so these options work for trace tree, and tracegraph. And the idea here is patterns. What do I actually want to see? You don't always want to see every single little subsidiary evaluation in your computation. So by default, one of the things that trace does is it only shows expressions after they get evaluated. This cuts down on the output, but sometimes it makes it so, I see that this evaluation gave this result, but what actually spawned that evaluation? One of the options that you can use is trace original. So if you do trace original goes to true, we're actually going to see every piece of the standard evaluation sequence. So if we look at this example, you start with fib of 3. Rather than going straight from fib of 3 to fib of 3 minus 1 plus fib of 3 minus 2, remember back to the standard evaluation sequence, you first have to evaluate the head and then each of its arguments. In this case, it's totally trivial. Fib is just fib. A symbol evaluates to itself if it doesn't have any own values. 3 evaluates to 3. It's a number. Numbers evaluate them to themselves. And so fib of 3, when you go through those first couple of steps of the evaluation process, just gives you a fib of 3 back. It's at that point transformation rules get applied. Usually you don't want to see this level of detail, but if you say trace original goes to true, you can get it. Another extension we made actually pretty recently is you can now say trace original goes to automatic. This will give us the smaller graph like before, where you only see kind of the interesting parts, but it makes sure that nodes get labeled. These nodes here are the expressions before evaluation. And so with trace original goes to automatic, we get to see what those expressions were, and in addition to the results that they give. Another thing you can do, there's more options than just trace original. I'd refer you to the reference page for the full list. Another thing is you can say there's only certain patterns that I even want to see. So for example, if I do fib of 6 without specifying what I want, I'm going to get potentially a very large graph. A lot of this, though, is things like 5 minus 1 goes to 4. Well, if I don't want to see those, and I'm only interested in the dependence between these different fib calls, you can give a pattern. So here in the second argument, I say blank fib. This means only show me the expressions with the head fib. And so when you evaluate that, you can see we got fib of 6, which depends on fib of 5 and fib of 4, but you don't see all of the steps in between or after. You know, you can change this pattern as much as you want to get just the expressions that you want. So far, I've been showing you how to get the entire execution history. Sometimes you want to actually do things a little bit more interactively. So we have a few options for that. One is trace print. Trace print, what it does is rather than returning the evaluation chains, it's going to print the expressions out as it encounters them. So here, so I don't get too much output, I'm saying just spit out the fibs. And so we see we get fib of 4, we get fib of 4 minus 1, fib of 3, fib of 3 minus 1, fib of 2, and so on until we get our final result of 3. And you can see there's very subtle indentation to kind of depict the nesting of evaluation chains that we saw earlier. Fib of 4 minus 1 is a subsidiary evaluation for fib of 4, and so it's slightly indented. So here the function that we're doing whenever we encounter the expression is just print. There's also trace scan for if you want to do something other than print. Here I'm using echo. So if I evaluate that expression, it's going to apply echo to the intermediate expressions that match this pattern. So I'm going to echo out all of the fibs. This could be reap, all kinds of side effects you might want to have. The last function I'm going to talk about for this talk is trace dialog. Trace dialog actually lets you go through the evaluation step by step, kind of a hybrid approach of trace print and trace. So if you evaluate this, you're going to enter what's called a dialog. So I'm now in a dialog. I have fib of 4. If I want to see what fib of 4 returns, evaluate return. Well, it returns fib of 4 minus 1. If I want to get out of what's the fib 4 minus 1 return, say return again, well, that's fib of 3, because 4 minus 1 evaluates to 3. And you can keep doing return, and you will keep going through the steps of the evaluation. So finally, we're now out of the dialog. All right, so that has been a tour through the built-in and third-party functionality we have for tracing evaluation, different visualizations, different ways of filtering. Yeah, so thank you for attending this talk. If there are any questions, I can take those now. It would be useful if you could share your notebook. Yes, I will make sure to upload the notebook right after this talk. Can you increase the indentation in trace print? I don't, I'm checking now. I don't know if it has an option to increase. It doesn't, look like there's a way to change the indentation, but I think the indentation is pretty minimal, so worth taking another look at that. Maybe making trace print a little easier to read. Can you apply this trace graph function to hypergraphs? Well, you can apply trace graph to any Wolfram language evaluation. So if you have some functionality involving hypergraphs, you would see the code as it gets called for that. You might be wanting instead something that kind of traces hypergraph evolution, which I'm not sure if that's what you want, but that's not the same thing as the standard evaluation sequence. So that would be probably a separate function that would be needed for that. Is there a keyboard shortcut for return? If there is, I don't know what it is. Could you use diff tools to compare different traces? As I understand it, currently diff tools is focused on sequence alignment, which is like a linear flat type of comparison. I think there's certainly interesting things we could do in the future with diff for trees, and these evaluation sequences are trees. So we should be able in the future to do something with diff to compare two trace graphs, or even just two outputs of trace. I think that would actually be useful. See what's different. Okay, I guess if there are no other questions, we can end it here. If anybody's interested in trace, feel free to reach out to me and I could provide more answers. All right, thanks.